Hello everyone, I am Surendra Jain, Master Teacher of Mathematics in Vedantu. I am teaching maths for last 14 years. I have been teaching students for JEE Mains Advanced, 𝐢𝐈𝐓, 𝒉𝒄𝐄 𝐻𝒐𝒻 and also for CMI-ISI. In these sessions, as I told in my last sessions also, I am picking few subtopics where I am sharing with you some short ideas, short tricks, some alternate methods by knowing which you will be able to solve questions faster. These ideas may not be available in certain books or maybe at other places. So definitely when you go through these sessions, you will find them useful to solve questions, especially exams like JEE Advanced. Okay, in today's session, I will be talking about counting twice from the topic PnC. Okay, before I start this session, I like to tell you one more thing. 𝒁𝒆, who got All India rank 15 this year in 2025, I think Shimon sir has discussed about 𝒁𝒆 in his sessions. He was student of RM 22-25. He was student of mine for 3 years and he got full 120 marks out of 120 in JEE Advanced 25. That's a very rare thing, students. In these sessions, we are targeting that few students from you will repeat that performance. So please go through these sessions. Let us know how you're feeling. Give your feedback in the comment section. Okay, so this counting twice, I'll start now. Looking little strange, but let me tell you, in permutation combination, we use many methods. One of them is counting twice. What are we going to do it here? We will be counting certain thing, certain number of ways, certain number of sets in two different ways. One way will be giving you certain expression, another way will give you some different expression. Now because they both are doing same thing, their values has to be same. So by first counting in two different ways, getting two different expressions, we will claim these two expressions should be same. To make you understand, I'll start with one very simple, one very easy example which many of you might be knowing it already. Here I am going to prove this NC0 plus NC1 up to NCn is equal to 2 power n. Now what I am going to do, I'll be taking a set of n objects, 1, 2, 3, 4, 5 and so on n. Okay, now on the right hand side it is 2 power n, on the left hand side it is NC0, NC1 and so on. This gives you the idea that we are selecting none elements or some elements or all elements. Okay, so when I am selecting no element, so it will be done in just one way, that is NC0. If I am going to select some element starting with just one, it will be NC1 ways. If you select two elements, it will be NC2 ways and so on. And if you want to select all of them, it will be NCn ways. Okay, now let's do it in some different way. Now let's go to the each element, let's say 1, and say yes or no in front of this 1. When I'm saying yes, 1 is selected. When I'm saying no, it is not selected. There is no other option. So I am having two ways to choose or not to choose this element. I think this is same for all the elements. I can go to these elements and saying yes or no and so on. And here also it will be yes or no in two ways. Now please see, if you call all of them as no, 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 this is equal to NC0 where no element is selected. If you say exactly one yes, okay, and all remaining as no, which can be done in actually n ways, because which element will be getting y, yes, and which other elements will be getting no. It can be done in n ways, which is precisely done by NC1 also here. Similar to this, you can see 2 y's, all rest no's is equivalent to NC2 and so on. Here, if I count this way, because every element is getting two ways for selecting or not selecting, so by a fundamental principle of counting, we can say it is 2 into 2 into 2, it is n times of 2 power n. Hence this has to be equal to 2 power n. So that is the idea. I think I have set the context. You will understand few other things very easily now. Okay, my next example here is this identity. This is very important identity. You must be using it in PnC binomial questions. If not, then please do remember it. Now today I will be telling you one very easy one-liner proof of it using counting twice. Okay, you don't have to struggle to remember this result anymore after this session. Okay, so what I'm going to do here, I will assume there are n plus 1 persons. Okay, out of which there is one teacher, let's say, and remaining n are the students. Okay, and we want to select exactly r people out of these n plus 1. If we want to select r people, I think it is direct n plus 1 CR. Okay, but now selecting r people now can be categorized in two ways, two cases. One, when teacher is selected, and another when teacher is not selected. I think there cannot be no other case for this teacher selected or not selected. If teacher is selected, then you are supposed to select only r minus 1 students from the n students. Okay, whereas if teacher is not selected, then you are supposed to select r students from the n students only, because there is no teacher selection. That means all r persons will come from n students. Now there is no other way, and either this will happen or this will happen, though that means we have to add these two. So if you add these two, we must get this thing. Now please look at this expression and see if it is direct or not. You will never ever forget this result if you use this method which I told you. In fact, this can be further extended to some more results also. Suppose you are having two teachers, then you may have three cases: no teacher selected, one teacher selected, both teachers selected. Then n plus 2 CR can be written as sum of three different expressions that you can do it yourself. Okay, so this kind of identities can be derived like this directly. Okay, now coming to this thing here, r into NCR is equal to n into n minus 1 CR minus 1. We mostly remember this like this also: n by r into n minus 1 CR minus 1, or n minus 1 CR minus 1 is equal to r upon n into NCR. I think I will go with this thing. Okay, but to derive this, I will use this result. I think they all are same thing, just the rearrangement. Now here what we are going to do, in the left hand side, as it is very clear, we are selecting r persons from n persons. Okay, so selection of r from n. Okay, now I will do it in two steps to get the right hand side. The first step is select 1. Select 1. So if you have to select 1 from n, I think it will be n ways. If you have to select one person, then I think it is just n ways. And then when one person is selected, okay, then there will be remaining n minus 1 people, n minus 1 people, and from those I will be selecting r minus 1 persons. Okay, that is done in n minus 1 CR minus 1 ways. Okay, so this left hand side is selection of r people. On the right hand side, we are first selecting one person, and then we are selecting r minus 1 from the n minus 1 people. Okay, so it looks like that NCR should be equal to, on the left hand side, should be equal to n into n minus 1 CR minus 1, but that's not correct. There's one simple thing, please try to understand, and I'll try to explain you this through taking r is equal to 2. Okay, r is equal to 2. So suppose from n people you have to select 2. Okay, now what I'm going to do next, I will be selecting one person from the n. That will be done in n ways, and then from the remaining n minus 1, I will be selecting the remaining person. But there is a problem. Suppose the person that was selected in the beginning in this n was, let's say, P1. Okay, and the second person that was selected from the remaining n minus 1 is, let's say, P2. Okay, but here when I'm saying n ways, this also includes those cases when P2 was selected first, and maybe in the remaining n minus 1 we select P1 there. So you can see the selection of P1 and P2 in this way is actually repeated twice. Why? P1 would have been first selected and then P2, or other order also. So here we have to divide by 2 so that repetition is accounted for. So here the same logic if I apply, so this r has to be dividing it to get this thing completely. So this result NCR is equal to n by r into n minus 1 CR minus 1 can come from there also. Okay, now if you remember it otherwise it's okay, but I'm just giving you the idea of this result, how you can do it by counting twice. See, whenever I'm telling you and you're not very comfortable with it, why I'm saying it? Because I felt while explaining it that I have to explain little much, but if you understand the concept behind it, I think it will be useful for you. Okay, now coming to the next thing, that is 1 into NC1, 2 into NC2, and so on. Okay, now to do this, I think now I can tell you two methods. So my first method would be it will be just the extension of previous two results. Okay, so I think this can be written as summation R into NCR, where R is starting with 0 to N. In fact, some people may say, I will not say 0, I will say from 1. It's okay, because if you start with 0 or you start with 1, because if you put 0, first element will be 0. So it's same thing. Now here, as you can see, using the previous identity, that R into NCR, I can write this as N into N minus 1 CR minus 1. Okay, and here R is starting with 1 to N. So you can see it is actually N you can take outside, that is the first identity, and I can write it directly R N into 2 power N minus 1. That is one method, but my method 2 is much better than this. Let me see how method 2 is working. Please understand, in method 2 what I am going to do, I am going to select 1 or 2 or 3 or n persons from n given persons, and this time I will call that selection as a team. So I am going to select a team of R from n. There are n persons, we have to select a team of R persons from n, where R can be 1 or 2 or 3 or n, and then choose a captain, then choose a leader or captain. Okay, now one leader is to be selected from these R selected people, because there is a team of R persons, from them only I will be choosing a leader, so that will be done in R ways. Okay, select a team of R, and selection of this team of R will be, I think, NCR ways. Okay, and from those R persons we have to choose a leader, that will be done in R ways only. So here you can see we are getting this result to be R into NCR. Okay, now if you vary your R from 1, then 2, then 3, and so on, we will be getting my left hand side. Okay, now let's see right hand side. What right hand side is doing? In this right hand side, we are actually selecting a captain first, a leader first, in n ways. Okay, and then from the remaining n minus 1 persons, you can use that yes no for all n minus 1 people, that is in 2 power n minus 1 ways. In this, if there is only no for all the n minus 1 people, you will be only having a captain, which is equivalent to having a team of 1, and that person itself is the leader. Okay, if you are having exactly one yes here, that means there will be 2 people. Okay, and that is equivalent to having team of 2 and one of them as a leader there. Okay, so you can see here we are first making a team, then selecting a leader. Here we are first selecting a leader, and then we are selecting their selecting the remaining team persons, 2 power n minus 1. So this is same. So I think this method is much faster than any other method. In fact, to prove it, we normally use 2 more methods. One is differentiation, and one is when you reverse the order and use the fact that NC0 is equal to NCN, NC1 is equal to NCN minus 1, and so on. So that method is also there. I will not talk about that. Here I will be talking about only counting twice. And I think this one is the best method. In fact, this opens the ways to solve other identities also. Here, please see, it is 1 into 2 into NC2 plus 2 into 3 into NC3, and so on. In fact, this left hand side is actually summation R into R minus 1 into NCR, where R is starting with 2 and going till N. Okay, now here it is a simple extension of this result. Simple extension of this result. How? Please see. Here I am claiming that first select a team of R, then select captain and vice captain. captain and vice captain. So selecting R person in NCR ways, selecting a captain in R ways, and selecting a vice captain that will be different from the captain R minus 1 ways. So this is my left hand side. Now please see on the right hand side, it is selecting captain first, then selecting vice captain, and then from the remaining n minus 2 people, select or not select them in 2 power n minus 2 ways. So this is also doing exactly the same thing which this entire summation is doing. So this becomes very direct. You can see n into n minus 1 into 2 power n minus 2. There is no need to use any other thing, although this can be done by 2 times differentiation or by using those identities that I told you in the number 3, or using that identity and then reversing the order. That way also you can do it, but I think this kind of analogy of or counting twice is direct. Okay, in fact, if you write R into R minus 1 into R minus 2 and then NCR, I think you will understand captain, vice captain, and maybe some other person, then 2 into n minus 3. So I think this kind of results can be derived directly. Okay, and this will be useful to solve questions like this. Here you can see this left hand side is actually summation R square into NCR, summation R square into NCR. Now you can do it in 2 ways. I will tell you 2 ways. One is that you can write it as R into R minus 1 into NCR plus summation R into NCR. Okay, R is starting with 1 going till n, R is starting with 1 going till n. Here you can write 2 instead of 1 also, because 1 is giving you just 0 only here, and here R is equal to 1 to n. Now we know it directly. That's a concept where we are choosing a leader and sub leader after selecting R persons, and directly it can be done in n into n minus 1 into 2 power n minus 2 ways. Whereas this is just selecting a leader after selection of R persons, so it is n into 2 power n minus 1. Just add them, and after simplification I think you get n into n plus 1 into 2 power n minus 2, if I am not wrong. Yeah, that's it. Okay, if someone wants to do it directly, that can also be done, but the problem here is because we are multiplying R with R only here, so it is consisting of those cases where captain and vice captain can be the same persons also in few cases. Okay, so you have to add the 2 things when captain and vice captain are different. Okay, plus when captain and vice captain they are same. When captain and vice captain are same, that means captain selection in n ways, vice captain selection in just 1 way, because same person will be the vice captain, and then we are having only n minus 1 people left. So 2 into 2 n minus 1 will come in this case. It is actually exactly same what I have done it here. Okay, so if it is R square, you can do it either this way or you can split in 2 parts and then you will get the result. Okay, so I hope you understand how this kind of questions can be done with that concept of counting twice. Okay, now this I have taken where a quadratic is multiplied with NCR. Now this thing can be done by taking summation R square into NCR. If you know this result, you can use it, plus B into summation R into NCR. I think this comes directly by that method of captain and team of R plus C into NCR. I think you know how this kind of questions can be done. Now to get this, you may use result. If you remember that result, this n plus n into n plus 1 into 2 power n minus 2, or you split as a case where leader sub leader are different or leader sub leader are same. So that way you can do it. Okay, in fact R cube thing can also be taken care of similar way. Okay, if you are looking for, let's say, summation R cube into NCR, so what you will do, you will be writing it as R into R minus 1 into R minus 2 into NCR. So R cube term is taken care of, but we have subtracted, is it subtraction? Yeah, subtracted R square term 3R times, I think. So I will be adding 3 into R minus 1. Let me just check. 2R minus r, so 3r square, so 3r square added, so r square term is taken care of. Now r term, I think 2r here minus 3r here, so I have to add r one more time here, so this will give you only r cube. So this r cube has written by 3 things. This is done now directly because there is the captain, sub-captain and sub-sub-captain maybe, and team of R people. This is captain, sub-captain, team of R people. This is captain, team of R people. So applying your counting twice logic, you can write this result directly, this result directly, this result directly to get R cube into NCR. So this way, I think this can also be done. And more than that, I don't think you will be needed. Although you are now ready, even if somebody is asking summation R power 4 into NCR to be found, that can also be done this way. Okay. Now this question. Now in this question, you can see instead of multiplication, division is there, and most of the people do it by integration or by using that identity that NCR is equal to n upon r into n minus 1 CR minus 1. That identity is also used, but here I will tell you counting twice, although it is not that obvious. Okay, so please listen carefully, and still if you are not comfortable, then do it by your own method. I don't mind with that because this is not that direct actually. So here what I will do, I will take this n plus 1 this side. I will take n plus 1 getting multiplied here. So this is not here now. Now if it is not here, it is multiplied here. You can see your right hand side is 2 power n plus 1 minus 1. Okay, which tells you it is actually number of ways of selecting at least one person from n plus 1 different persons. There are total 1, 2, 3 and so on, n plus 1 persons, and you are saying yes, no to all of them. That will be 2 power n plus 1 ways, out of which one of the way would be where we are saying no to all of them. I am subtracting that. So I am in a way saying at least one person is selected in this 2 power n plus 1 minus 1 way. Now let us see if it is working out here or not. My first term is we are selecting one person from the n plus 1. Okay, so that will be n plus 1 ways. And if only one person is to be selected, so this will be multiplied with NC0. From remaining n person, 0 is to be selected. But if after selection of one person, that is done in n plus 1 ways, you select one more person from the remaining NC1 ways, so that will be n plus 1 into NC1. But if you remember, I told you here also this thing. I multiplied by 1 by 2, or I divided by 2 to take care of the repetition. I'll show you, I'll explain it here also why I'm dividing by 2. Suppose your first person selected is P1, which is there in n plus 1 ways, and then from the remaining NC1 you are selecting P2, but this P2 P1 can change their order, where P2 selected in the first place and P1 selected in this NC1. So the same selection is happening in 2 ways, but we have to count it as 1, so divide by 2. Similarly, if you select 2 more person after selection of 1, that will be NC2, but here now there are 3 people, P1, P2, P3. At first place it could have been P3 also, so there will be 3 ways to get the same thing, so that's why we are dividing it by 3. So this is how this entire thing is coming, and this will be equal to 2 power n plus 1 minus 1. Okay, I'm again repeating, I'm again saying that if you feel that method of integration is better for you, it's okay. There can be other method also where you write NCR upon r plus 1 as n plus 1 CR plus 1 upon n plus 1. Okay, that is also a method. So if you use that, then also it is fine. In this, every term will be giving you n plus 1 common. Okay, and the summation of n plus 1 CR plus 1, where r start with 0 going till n, will give you all the terms which adds up to 2 power n plus 1 other than n plus 1 C0, so minus 1 there. I think you know this method. I'm just focusing on my counting twice method here. Okay, one more thing, as I told in my previous sessions also, you must have seen my session notes. Here also I will be giving you all the session notes with possible explanation of all these things. So please go through it. Okay, that will be useful. Now this identity, Wenders-Mondi's identity, very famous identity, you must remember it. Okay, now it will be very good to know that this can also be done by counting twice. How? Let's see. So here on the right hand side we are having 2 NCN, here we are having NC0 square, NC1 square, and so on. What I am going to do, on the left hand side I will write NC0 square as NC0 into NCN. NC0 into NCN. Here I will be writing it as NC1 into NCN minus 1, because you know NC1 and NCN minus 1 are same. Then NC2 into NCN minus 2, and so on. In the end it is NCN into NC0. Okay, so this is my left hand side. Now to create that analogy of counting twice, I will take n girls and n boys, n girls and n boys. Okay, now here there are total 2n persons. On the right hand side, if you do it directly, we are selecting total n persons. Select n persons. If you are selecting n persons, I think it is directly 2NCN ways. Okay, but let's try to break into the cases. Here you are selecting 0 girls. You are selecting 0 girls, all boys only. Total n persons. NC0 ways for girls, NCN for boys. This is for just 1 girl and remaining boys. Maybe I can write 0 girl, n boys, here n 1 girl, n minus 1 boys. So NC1 to select that 1 girl and n minus 1 boys, for selection of n minus 1 boys, NCN minus 1. Similarly here it is 2 girl and n minus 2 boys to be selected, and so on. Here it will be all n girls and 0 boys. Okay, now you can see if you are selecting n persons out of 2n, where n are girls, n are boys, I think there is no other case left other than this, isn't it? So this has to be equal to 2NCN. So much obvious thing. Now you are doing it by coefficient method, writing 1 plus x power n and then x plus 1 power n, and then trying to compare the coefficient of x power n. That is a very good method, no doubt about that. But you can see the simplicity and the, I will say, the time required to solve or to use this method. I think tremendously less time here than as compared to the coefficient method. In fact, all such kind of questions I'll show you here can be done by this method. Here you can see NC0 NCK, NC1 NCK plus 1, and so on. Here you can see on the left hand side there is a difference of k, 0k difference of k, 1k plus 1 difference of k, and so on. So what I will do, first I will write this as NC0 and NCN minus k. Then I will write this as NC1 into NCN minus k minus 1, and so on. This one I will be writing NCN minus k into NC0. Okay, now you can see after changing one NCK or 1CN NCK plus 1 like this, the sum of these two becomes same, n minus k. Sum of these two becomes same, NC minus n minus k. Now, so what we are going to do here, we will be again, we will be taking case of that thing, n girls, n boys. Okay, and we will be selecting n minus k persons, n minus k persons to be selected. So that will give you my right hand side. Let me first focus on this. If you are going to select n minus k persons, so that will be 2NC n minus k. Now if you are selecting n minus k persons, then it will have cases where no girl is selected, 0 girl, okay, all n minus k boys. Okay, then 1 girl, n minus k minus 1 boys, and so on. N minus k girl and 0 boys. This is clear, I think. There is no other possibility, because if total n minus k persons are there, so this will be distributed among girls and boys only. So 0 girl with n minus k boys, and like this. So this has to be equal to this thing. Now by the property of NC, R is equal to NC n minus R, I think we can write these two also equal. So that is direct. Okay. So coming to the next identity. In this case, what I have done, I have taken m here and n here. And here you can see 0k, 1k plus 1, 2k plus 2, the difference is of k. And as I did in my previous result, I will be changing nck as nc n minus k, so that the summation here is same, nc n minus k minus 1. Summation of this 0 n minus k or 1 with n minus k minus 1, they all are same, mc2 into nc, it will be n minus k minus 2 and so on. Now in this case, what we will be doing, we will be taking m girls and n boys, and we have to select n minus k. The sum is n minus k, so we have to select total n minus k persons. If n minus k persons to be selected, that means it should be 0 girl n minus k boys or 1 girl n minus k minus 1 boys. So this is how this is applicable to this also, where this number m, this number n, they are different. Okay, I think it's simple. In fact, in that coefficient method also you're doing the same thing. Just one thing I would like to tell you, in the previous question also I was about to tell this thing, that you have to make sure that whenever you are selecting n minus k, no case is left out. Suppose some case is left out, then these two sides will not be equal. Here, if n minus k persons are to be selected, I think all cases will be accounted for, starting with 0 girl, 1 girl, 2 girl, and in the end n minus k girl. Suppose n minus k becomes more than m. Okay, that means that selection will not be possible. See, m and n are different. So it's quite possible that whatever k we are selecting, suppose n minus k becomes bigger than m. So those many cases which are irrelevant, where n minus k becomes bigger than m, these terms will be just 0, 0. You have to take care of only those terms which are, valid terms. The other terms will be just 0, and that sum has to be equal to this thing, no doubt about that. So what I'm saying, that whatever m, n, k you are using, you have to make sure that all the possible cases you have accounted for. Otherwise these will not be equal to 0. Suppose you forgot to take the case of that 0 girls, then I think this term will be this term. If it is not there, then these two things will not be same. So I'm just giving you a warning that you are supposed to take care of all the cases. If some cases are irrelevant, they becomes beyond the domain, you can say. Here I think they will be just 0, 0. So it is safe to write from this to this. Even if some case becomes like n minus k is bigger than m, I think this becomes just 0. Okay, so no need to worry about that case. Okay, in fact, now you can see this 10, this identity in this 10 is a general case, and 9 is a special case of that, where m becomes equal to n. And going backwards, this identity is a special case of that 9th one, where I am writing k equal to 0. So actually, if you know this, okay, you can derive 9th one, you can derive 8th one also directly. But the fundamental thing here is actually counting twice. So you can directly get those results of 8 or 9 or 10, whatever comes. Okay. Okay, now here you can see this is a combination of Wenders-Mondi identity, and some numbers 1, 2, 3 and so on are also multiplied here. Okay, now to understand the left hand side first, I can write it as n into nc1, nc n minus 1, then 2 into nc2 and nc n minus 2 and so on. Okay, then let's try to understand what exactly this is doing. Okay, maybe if I take n girls, n boys. Okay, so here I am selecting 1 girl and I am selecting n minus 1 boys. Okay, so total n persons are selected, but 1 is also multiplied. So maybe what we are saying, that first you select n persons in which 1 girl is there, and then make that girl as a captain or leader. Okay, this leader will be from girl only. Now similarly here you can see that you are selecting 2 girls, you are selecting n minus 2 boys. Okay, and from the 2 girls we are making the leader. Okay, and it can be done in 2 ways because we are having 2 girls. Now same thing is happening everywhere. So it is like the number of girls that we are selecting, the leader is coming from there only. Okay, also you can see if I go till the last thing, this is NCN into NC0 and n multiplied here. So here you can see n girls, 0 boys. Okay, and leader is from the girls. Okay, so what this left hand side is saying, it is saying that at least 1 girl is to be selected. Okay, and total n persons are to be selected. Okay, and leader is to be made from the girls. Okay, now let's see what right side should be now, because we have to select a leader from girls. So let's choose a captain or leader from n girls in n ways. Okay, and then there is no restriction. After selecting 1 girl as a leader, you are free to choose or not to choose any girl or not any number of girls. So that will be 2n-1 cn-1, because now remaining n-1 girls and remaining n boys, total 2n-1 people, we have to select n-1 persons. So this is how this identity is coming directly. I hope that is clear to all of you. Okay, now coming to previous year questions, in fact my first question is directly based on this question only, which I have told you just now. 1 into this, 2 into this, 3 into this, and so on. So if you write this as 10C1 into 10C9, this as 10C2 into 10C8, and so on. So this is like total 20 people, 10 girls, 10 boys. Okay, and at least 1 girl is to be selected, captain to be selected from the girls. So there will be 10 ways to select the captain, and then 19C10, because total number of people selected are 10. So this entire result will be 10 into 19C 19C10. Okay, and if you solve it, they are asking just this divided by 1430. I think this comes out to be 646. If you divide this by 1430, this comes out to be 646. I think this is a simple calculation. Actually, this calculation is little bigger, because 19C10 if you write, you have to multiply many number of terms, but 1430 you factorize and you simplify it, it can be done. Okay, so you can see this question is very much direct if you use this concept of counting twice. Okay, now one more question from previous year 2019. Here you can see these terms, the determinant of this they are giving. So my first term, I think you know it, it is n into n plus 1 by 2, summation of first n natural numbers. If it is starting with k equal to 0, so that 0 will be 0 only, so 1 plus 2 plus 3 and so on. Now this is same thing which I was talking about, k square into nck. If you remember that result, fine. Otherwise also you can derive it very fast now. Okay, now this is that captain and team of k people, so it will be n into 2 power n minus 1. And the last one is, I think, binomial expansion of 1 plus 3 raised to the power n. So this will be 4 power n, and this they are giving you as 0. Okay, so I think here the counting twice is used here, and after that you have to solve it. There is no other shortcut, you have to solve it. So I think if you solve it, this into this will be n into n plus 1 by 2 into 4 power n, and this is equal to 0. So I can write this is equal to multiplying this into this. So n into n plus 1, I think this I can write as n square, and if I multiply these two, I will get 4 power n upon 8. I can write it as 2 power n upon 4, 2 power n upon 2, so upon 8 here. 4 power n will get cancelled, n into n plus 1 will also get cancelled. So we will be getting here, I think only n is left. The value of n comes out to be 4. Okay, yeah, n is coming out to be 4, and then they are asking NCK upon k plus 1. I think this also we did using counting twice, or you can use other method also. I think the result for this is 2 power n plus 1 minus 1 upon n plus 1. So if you put n is equal to 4, so this will be 2 power 5 32 minus 1 31 upon 5. So 6.2 is the answer of this question. Okay, so for this again I am saying, for that I told that time also, if you're comfortable with integration or other method, it's perfectly fine, but there exists counting twice for this also. Now this question, this was 2020, good question. Here first they have defined SCR, NCR they have defined, and you can see whenever R is less than or equal to S, it is given by this expression, and if it is greater than S, this is equal to 0. The same thing which I was talking about there, that whenever you feel that some terms are coming which are not relevant because your in NCR R becomes more than N, it will be just 0. Okay, so they are giving R and S as non-negative integers, so they have taken care of everything. Now for positive integers M and N, we are defining G of M N by this, and F M comma N comma P is given by this. So first we will start with this F of M comma N comma P. Okay, so here this thing is MCI. Okay, into, if I open these two by that expression that they have given, and in fact that's a standard result, it will be n plus I factorial upon p factorial into n plus I minus p factorial into that remaining thing is p plus n factorial upon p minus I factorial, and if you subtract it, you will be getting n plus I factorial here. So n plus I factorial, n plus I factorial is getting cancelled here. Okay, so what we are getting here, p plus n is independent of I. My I was starting with 0 going till p, so I can keep p plus n out of this summation sign, sigma sign. In fact, this p factorial can also be written outside. Okay, and summation, this MCI will be written here. Now please notice it here that these two terms, if you take the sum of them, it becomes n factorial. So if I write n factorial here, okay, then combining these two, which is n plus I minus p factorial into p minus I factorial. Okay, for that I will have to divide by n factorial, and because n is independent of I, so I can keep it outside. Okay, now you please see, this is becoming p plus n cp or cn you can write, whereas this summation is MCI into NCP minus I, p minus I. And as I told you there, when sum of these two is fixed, and because I is ranging from I equal to 0 to n, so all possible values are taken care of, because if you put I is equal to 0, it will be p. If you put I is equal to n, it will be p minus n. Actually this was p, not n, this was p. Yeah, so if you take I is equal to 0 to p, all values, all permissible values are taken care of. Okay, so here this will become equal to, now you can write it directly, p plus n cp, and this you can write it as m plus n cp. You can say m girls and boys. Okay, total number of people to be selected as p. You can break this into cases, and if you add all of them, you get this thing. So my f of m comma n comma p is coming out to be equal to this thing. Now they have defined G by this, so if you use the definition of f and you write G, it will be summation of this divided by this. So n plus p cp will get cancelled, so we are only having m plus n cp, and here p is ranging from 0 going till m plus n, and I think this is that first identity which I discussed today. It is equal to 2 power m plus n, 2 power m plus n, because all terms m plus n c0, m plus n c1 up to m plus n c, m plus n are coming here, so 2 power m plus n. Now this is what we have got for m plus n. So for g of m plus n, actually So you can now see if G of m comma n is equal to 2 power m plus n, which option should be correct? I think m n and m should be same, so A has to be correct, B has to be correct because it is just dependent on the sum of these two. Okay, here if you take 2m 2n, okay, so what will this be? This will be 2 power 2m plus 2n, okay, which we can write it as 2 power m plus n whole power 2. So actually D is correct, because then you can write this as G of m comma n whole square. So this is correct. A, B, D should be the answer of this question. Okay, now I have taken one more question. In fact, after that there is one more question, so total 2 questions in the session now. Here you can see 3C0 11C4, 4C3 10C4, 5C3 9C4 and so on, and this is given as x, c, y. Then we have to find x plus y. Here you can see not only these numbers are changing, but numbers are changing here also. 3 plus 4 7, 3 plus 4 7. Below numbers are such the sum is same. Okay, so maybe we could have used that n girls n boys analogy, but the problem here is that 3 11, here 4 10, but sum is same. 3 plus 11 14, 4 plus 10 14 and so on. Okay, so we have to think something else here. Okay, now to do this question, again, that is not very obvious. In fact, whenever I have given this question to my students, they have taken lots of time. In fact, some of them have done it by some coefficient method, but not by counting twice. So I'll be giving you that idea which I used when I solved this question first time. Okay, so here what I'm going to do, I will use beggar coin method. But before that, let me tell you what is beggar coin method. If you are having r beggars, okay, and n coins, when n coins means n identical coins. Okay, so r beggars, n coins, and there's no condition that any number of beggars may not be given any coin. Maybe you can give all the coins to one beggar. The only condition is that you have to distribute all the n coins. I think there is a direct result, and that is n plus r minus 1 c r minus 1. I think this is the result, to distribute n coins to r beggars so that any number of beggar can go empty. You may give all coins to maybe one beggar. So considering that, only condition is that all coins to be distributed is done in this way. Okay, I will be using this here. How? Please see. R minus 1 is coming here. So I will be saying there are 4 beggars and there are 5 beggars. Okay, let's say these are 2 sides of road. On one side there are 4 beggars, they are sitting every day. There are 5 beggars on the other side of the road. Okay, now if I have to get this 3C3 term, okay, 3C3 terms means I will be putting n is equal to 0 here. If I want 11, I think I should put n is equal to, because in this case r is 5, so that will be 4. My n should be I think 7 plus 5 12 minus 1 11. Yeah, correct. So in first case, what I'm doing, I'm giving 0 coins to one side of 0 coins to 4 beggars of one side of the road, 7 coins to 5 beggars on the other side of the road. Then I'm giving n is equal to 1, n is equal to 6, and so on. N is equal to 2, n is equal to 5, and so on. N is equal to 7, n is equal to 0. Now you can see my second term is corresponding to this. When one coin is going to 4 beggars, so 4C3 ways. 6 coins are going to 5 beggars, so 10C4 ways. Same formula. Similarly, the third term is coming for this case, n equal to 2, n is equal to 5. If you put n is equal to 2, you get 5C3, n is equal to 5 for 5 beggars, so you get 9C4. Similarly, the last term is for this last case, 7 plus 4 11, so 10C3, and 0 plus 5 minus 1, so 4C4. So you can see this left hand side is actually counting those cases where 4 beggars on one side of road and 5 beggars on the other side of road are given total of 7 coins. Total of 7 coins, and total 7 coins can be broken down only in these 8 cases which are on your left hand side. Okay, but now let's assume these are not one side other side, it is just total 9 beggars. Total 9 beggars, and we have to distribute 7 coins to them. 9 beggars and we are having 7 coins. Okay, that will be done in how many ways? 9 plus 7, 16, minus 1, so 15, and C8. So 15 C8 can be, if you consider all 9 beggars as single bunch of beggars, you can say, and 7 coins to be given. Okay, so you can see these 9 beggars, if divided into 2 sides of the road, this left side is doing the same thing, which right hand side equal to 15 C8 will be doing if we consider them as a single bunch of beggars. So X C Y should be this thing. It can be 15 C7 also, because when they are saying value can be, so it can be 15 C8 or 15 C7 also. So X plus Y would be either 22 or 23. So there can be 2 answers, B and C, for this question. See, this counting twice thing is a practice. It's something that you should practice in questions. You should try to give your thought, maybe this can be done by this method or not. Maybe sometimes you will be able to do it, sometimes you will not be able to do it. But at least for many standard problems, as I have shown you in previous year questions also, they are asking questions based on those standard results which are coming directly from this counting twice. So at least that idea of leaders, sub leaders, you should know. Selection from girls, boys, you should know. Okay, in fact I will suggest this beggar coin also you can keep in your mind while solving the questions. It will make things simple for you. You can do it by coefficient method, which I will not discuss it here. So this is how I am doing it, by counting twice. Now this question, actually this is second last question, because I think I am having this question as the last one. So this question is again combination of, as I told you, Wenders-Mondi identity. If you remember, we did a multiplication in one question. Here we are doing the division. So this question again, what I will be doing, I will be writing NC0, NC1, NCN upon 1, and this n plus 1 I will be bringing it here, and then you can see if it is giving you result directly or not. Okay, what will this be on the right hand side? It will be 2n plus 1 Cn plus 1. Okay, so we have to select n plus 1 people from 2n plus 1 people. Okay, and on the right hand side, if you see, we are dividing NC0, NC1. So probably what we have to do, we have to take n person maybe as a girl, n person as a boy, but there are total 2n plus 1 person. So what I will be doing, n plus 1 girl and n boys I will be saying. Okay, and when you are having this kind of configuration, so total there are 2n plus 1 persons. Okay, and if you select n plus 1 people, okay, I think there has to be one girl. You cannot select n plus 1 persons from 2n plus 1 without having at least one girl, because total number of boys are n only. So this right hand side is number of selections of n plus 1 people from these many of persons. Now on the on the left hand side, because one girl has to be there, so n plus 1 is for that only, that one girl selection is this n plus 1, and then after from n boys, n girls, you are doing NC0, NC1. Okay, then NC1, NCN minus 1, and this division by 1 and 2 I have told you 2 times in this session itself is because of the repetition of selection. Because when you are selecting some girl, let's say G1 in the beginning, okay, and then you select another girl G2 in this NC1, you could have selected G2 first and G1 later. So same selection is actually happening, but we are counting it 2 times, so we are dividing it by 2. Similarly, in the next case it will be divided by 3 and so on. So overall, if you count this, it has to be equal to 2n plus 1 Cn plus 1. Okay, in this question once again I will say, if you're not comfortable with this thing, although I will say think over it, I think it will be looking like obvious thing, not very difficult. But if you're not, then I think you can use the property where NC0 upon R, NC r upon r plus 1, sorry, r plus 1 can be written as n plus 1 c r plus 1 upon n plus 1. So the other method could be this also. In fact, let me do it by another method. Please see. So what we are having here, our result was summation NCR square upon r square, r plus 1 square, r plus 1 square actually. So NCR square upon r plus 1. So I can write this as NCR into NCn minus r upon r plus 1, and this I will be writing it as n plus 1 outside and summation n plus 1 c r plus 1. Okay, here r was starting with 1, was starting with 0 going till n, r is starting with 0 going till n, and this I will be writing NCR. Okay, no, NC n minus r is fine, NC n minus r is fine, so that sum of these two is same. Actually the sum is n plus 1. Okay, now if you use that counting twice thing, okay, you can say it is like n plus 1 girl, n boys, r starting with 0 till n. Okay, so here we will be getting 2n plus 1 c n plus 1. Okay, if you put r is equal to 0 and going till n, I think you can check all cases of this 2n plus 1 c n plus 1 is taken care of. Please see, in this, if I put r is equal to 0, you are selecting 1 girl, and here you are selecting n boys. Okay, if you put r is equal to 1, r is equal to 1, so you are selecting 2 girl and n minus 1 boys. This term is for girl, this term is for boy, and so on. If you put r is equal to n, so it will be n plus 1 girl, and that will be 0 boys. Okay, so you can see, if you are going to select n plus 1 persons out of 2n plus 1, I think that is the only possibility, because at least one girl has to be there. So this summation, because it is considering all possible cases, will become equal to this 2n plus 1 cn plus 1. Okay, so this is how this can be done after this also. Okay, so just last question, bacho. I have taken this deliberately. This is the again question based on PnC functions and inclusion exclusion principle. Let's see how this is done. If you see on the left hand side, it is saying NC n power n minus NC1 into n minus 1 raised to the power n, and so on. And on the right hand side, it is just n factorial. So to give you the idea, what I will be doing here, I will be making 1 onto functions from the set having n element to n element. Okay, now if you want 1 onto function, it has to be n factorial from set A to set B, or set A to set A also you can say. Now if you do it otherwise, let's say I just have to create functions. Okay, then every element will be having n choices. So 1 is having n choices, 2 is having n choices, so n power n will be total number of functions, but this will obviously not be 1 onto function. So we have to subtract those cases when few of the elements are left out. Okay, now which element is left out? This can be selected in NC1 ways. Let's say 1 is left out or 2 is left out. In that case, every element is having n minus 1 choices. After 1 is left out, this 1 will be having only n minus 1 choices, 2 will be having n minus 1 choices. So for all of them, you are having n minus 1 choices, and they will be multiplied n times, so n minus 1 power n. Okay, then I will not go into inclusion exclusion principle, because that is not the objective in this session. But you know, when we are doing this kind of cases, we over subtract. So for that, we have to add those cases when 2 elements are left out. So NC2, 2 elements, which 2 may be 1 with 3 or 2 with 7 or whatever. NC2 is to choose 2 elements which will not be selected, and then n minus 2 ways to connect every element of A here, and this raised to the power n. And once again, here you need to subtract, because in the inclusion exclusion principle we have plus minus, so this will be NC3, and here it will be n minus 3 power n, and so on. Okay, so if you keep doing like this, this thing in the end will become equal to n factorial only. So you can see we are counting same thing, that is number of onto functions for this thing, and one by inclusion exclusion principle, one by directly n factorial. So you are getting the you are getting same result for both of them, and hence they should be equal. Okay, so that's all for today, bachcho. I hope you will like this session, and I'll be sharing my session notes in that comment box, so please go through it. And that's it for today. I'll be bringing one more session very soon, maybe after 2 days or 3 days. So thank you so much. Bye everyone, take care.